Good morning or good afternoon, ladies and gentlemen, depending where you're joining from. This is Belén Gallego from ATA Insights here in Madrid. And I am delighted to be here with you today, where we explore the new topics, the innovation within the energy industry. It is always difficult to really understand what is going to be the full impact of this type of really futuristic technology into an industry. Today we're looking at artificial intelligence, but it's just part of a series where we're looking at data, where we're looking at Internet of Energy. So it's very difficult to tell, what is going to be the real impact in a few years. What is clear is that it's going to be transformational and that we need to be up to date and actually leading in this transformation so that we can actually get the full benefits of it. With me today, I have two experts on the topic. We have on the one hand, Alejandro Delgado, and on the other hand, Michael Liefman joining me. And I'm going to ask them to introduce themselves really briefly and tell us also where they're joining from. So Alejandro, please, can I ask you to introduce yourself?
Good afternoon. My name is Alejandro Delgado, and I'm the technical project manager of Aleasoft. The presentation I will show is about artificial intelligence applied in the energy sector, specifically for the energy price forecasting, and I'm talking from Barcelona, Spain.
Hi, everyone. Good morning or good afternoon. I'm Michael Liefman. My consulting practice is called Tenley Consulting. I'm based in Washington, D.C., and today I'm going to discuss the broad uses of artificial intelligence in the power sector. So I guess Alejandro will be much more specific, and I'll give a wide range of use cases.
Thank you very much. Both Alejandro and Michael actually know a lot about this topic, and they work with different companies on this as well. So I just wanted to take a little opportunity here to say hi to some of the people who've been using the chat to say hello. So I can see Christian from Germany. Christian is an old friend, and I'm glad to see you here again. We've got Fatima from Faisal from Fatima Group in Pakistan. We've got also Armin from Anar Khan in Canada. We've got Francisco Silva from France, from Paris, and also Laima Clemens from Colombia. So there is a bit of, people from everywhere, and we're glad to see. Please keep sharing. And without further ado, I'm going to ask Alejandro, please, can you share your screen? And whilst Alejandro actually gets his screen ready, just to remind you, the way that we're going to do this is first Alejandro is going to give a speech, then Michael is going to give his speech, and then we'll proceed to questions and answers. So please send your Q&As through the Q&A box at the bottom, and keep saying hi through the chats. And without further ado, Alejandro, please go and start.
Okay, so Aleasoft was founded 19 years ago as a spin-off of the UPC, the Polytechnic University of Catalonia. It started with a PhD in artificial intelligence of the current Director General, Antonio Delgado. We started developing forecasting models for the electricity demand, first in Spain and later for other countries throughout Europe. Some years later, with the liberalization of the European electricity markets, we started developing forecasting models for the energy price, first also for the Spanish market MIBEL, and currently our portfolio of forecasting models covers all the European markets. We have clients, all types of companies and players in the energy sector, including several TSOs like Electrification in Spain, Terna in Italy, Statnett in Norway, and Elia in Belgium. But also some of the biggest companies that trade electricity in the European markets look at our forecast. Some of them are Endesa, E.ON, Enel, Iberdrola, Gas Natural Fenosa, among several others. The methodology we developed specifically for the energy forecasting was called Alea Model. And Alea Model is a hybrid methodology that takes advantage of the latest developments in statistics and artificial intelligence, overcoming the limitations when they are used individually. The outcome is a forecasting model with the power of the artificial neural network and the efficiency of the Salim structure with multiple regression, capable of capturing the seasonal dynamics and evolution of time series with the capability to adapt to changes in tendency. The neural network, using machine learning techniques, the model looks for dynamic relations of the data, project them into the future, and obtain the best possible forecast. The ALEA model combines several statistical techniques. Among them are regression, Box and Jenkins method, hydrothermal model, and econometrics. For instance, the regression analysis to estimate the cause-effect relation between the explanatory variables and the main variable, and also among the explanatory variables themselves. With the use of the regression structures, the regression allows the introduction of non-linearities in the models. On the other part, the Box and Jenkins method that uses the Salima structure to analyze time series and apply differential transformations to make them stationary. This method integrates the capacity to use seasonality in the models. For the part of the hydrothermal model, for price forecasting specifically, this model statistically fits the demand gap left by renewables and nuclear production, and it takes into account the cost of producing energy with the thermal and hydro technologies. Also, the use of econometrics that integrates socioeconomic variables like GDP, industrial production, unemployment, and population growth, specifically for energy demand and price forecasting. So all these statistical techniques are integrated with recurrent artificial neural networks that uses machine learning algorithms to incorporate autoregressive and moving average in the neuron's transfer functions. With both regular and seasonal terms, they incorporate non-linearity into the transfer functions to accommodate non-linear dependencies with the variables. Altogether, it represents one of the most scientifically advanced structures of transfer functions for time series forecasting. The forecasting models we have developed are not limited to energy demand and price, but we are also providing forecasting for any variable related to the gas and energy sector, like the consumption of a portfolio of clients for retailers, weather variables like temperature, cloudiness, wind speed, and solar radiation, socioeconomic index, fuel prices, CO2 emission rights, renewable energy productions like wind power, photovoltaic, thermosolar, and hydroelectric, among others. We classify our forecasting horizons in three: short term, which is up to 19 days ahead, mid-term, up to 3 years ahead, and long term, which is up to 30 years ahead. For all these horizons, we provide price forecasts with early granularity, not only for the mean scenario of the variable, but also with their associated probability distributions. Lately, our long-term price forecasting service has been the most demanded from our clients due to the several PPAs that are signing up throughout Europe. This is a very important tool for power constructions or energy risk management, among others. Finally, I wanted to share this example today in order to better illustrate how our methodology works. This long-term forecast was generated in November 2010 for the Spanish market price. The black curve being the registered market price up to last month. If you look at the historical data at the time when the forecast was made, you can see the high variability the curve presents up to that point. Learning from all the data of the explanatory variables, the ALEA model was able to determine the equilibrium point and project it into the future. As you can see, the forecast is still valid today. Thank you very much.
Thank you very much, Alejandro. You didn't take much time at all. You were really short and precise. So I'm sure there's going to be plenty of questions about your presentation. I have some as well. So I would appreciate if you can take your screen off at the top, just press, perfect. And I'm going to ask Michael also to share his presentation. And in the meanwhile, just let me tell you that we are recording this session. We are going to send you the presentations and please use the Q&A box. Let's get some questions going. Thank you very much, Michael. We can see it perfectly.
Wonderful.
And we can hear you, so go ahead.
Perfect. So again, thanks, Alejandro, and for giving me all this extra time. So I'm going to talk about AI in the power sector. So Tenley Consulting is my practice, as I mentioned before, and we do a variety of things from strategic planning to scenario building to tech trends analysis, et cetera. And you can see my website there, and let's get into the presentation. So what I like to start with is this big number, 40%. For me, this is what gave me the huge aha moment that the application of AI to the power sector has great potential. So many of you, if you've seen any news clippings or news stories about artificial intelligence, may have heard this story a few years ago when one of Google's AI departments, which is DeepMind, it was a firm in the UK, beat the then reigning champion at the game of Go. This surprised many AI scientists. They didn't think that Go AI could beat a human Go player, and they thought it would be another 5-10 years at least before that happened. So this was sort of a seminal moment in the trajectory that AI has been on in the last few years. That same team from Google, DeepMind, decided to apply a similar set of algorithms to their own internal problems. So Google, like every other major internet company or major data company, has data servers, data farms, server farms, whatever you want to call them, that use up an enormous amount of energy. For energy people like me and Belen and Alejandro, and I'm sure many of you on the webinar, the notion that server farms data centers use an enormous amount of energy is an old problem, and it's one that we hadn't really been able to solve well. Tinkering around the edges, slightly better air conditioners, slightly less energy using computing systems, but there were kind of minimal improvements. DeepMind set its team onto the problem of how to reduce energy usage at these data farms, and the numbers were sort of startling. So there was a 15% reduction in overall electricity usage and a 40% improvement in energy efficiency. So these were huge numbers. It started out with, I think, 21 variables across all the different possible combinations of changing the heating, to changing the ductwork, to changing the flow of which server is used when. And it started out with a recommender system. In other words, the system would say, hey, guy that's operating the server farm, change this parameter. Little by little, they've been moving to an increasingly automated system, taking the humans out of the loop, and are continuing to improve energy efficiency across the data centers. So that's, for me, that was story number one. Story number two was that shortly after they published this paper, Google started talking to the national grid in the UK with a proposal to apply these same kinds of algorithms, obviously much more complicated and much more sophisticated, to the UK grid in general, with a goal of reducing energy consumption, or improving energy efficiency, I should say, by 10%. So 10% may seem like a kind of small number, but if you think about what happened in the 2008, 2009 recession, there was a really substantial drop in energy usage in the UK. I think it was maybe 4%, 5% at most. And that caused ripples throughout the UK power system. A lot of power plants were no longer economic. So you can imagine a 10% reduction would have major impacts. Google is now beginning to think about applying the same sort of algorithms to different industrial sites. There are applications to grids that are somewhere between a data center and a full grid, and we'll talk about that as we go through the presentation here. But the main takeaway is AI is applicable everywhere across the power sector, and it is being applied little by little everywhere across the power sector. It doesn't have a single specific use. I'll talk a little bit about some definitions, and I'll go through several examples of where I think AI use is interesting. And I'll end with this notion of autonomous energy grids, which is beginning to be researched. It's a little bit futuristic right now, but it might be where we're headed. So definitions, I'm not going to read these. If you've looked at all for definitions of AI, I'm sure you've found dozens. These are two that I find particularly useful. Sometimes people confuse or conflate AI and machine learning. They're not the same, they're closely related, but they're sometimes used interchangeably. The parts of these definitions that I think are important are the foresight in its environment, right? So it enables an entity to function appropriately with foresight in its environment. And Alejandro gave some really excellent examples of how that's used within energy forecasting. And machine learning, again, the part of this definition that I think is particularly crucial is improve their learning over time in autonomous fashion. And so meaning that the algorithms that are at play here get better and better, and they do so essentially by themselves. There's some training involved to get the algorithms up to readiness, and then occasionally there's a continued training across the way. But basically, the algorithms are functioning autonomously. And beyond that, I'm not going to go into any technical details of deep learning or any of the different subdomains or sub-techniques. So the first thing I want to point out is that AI is in energy across the entire supply chain, all the way from the top OEMs to individual consumer devices. So at GE, there's this industrial Internet of Things, IoT, right? Linkage of design and engineering and manufacturing and supply chain and distribution and services. So for example, according to GE, their manufacturing system, here I'm talking about actually building the machines, not even using the machines, but building the machines will result in Vietnam, for example, a 5% increase in productivity in their factory, in a wind generator factory. So again, this is building the wind generators. In Muskegon, they had a 25% better on-time delivery rate. So this has nothing to do with how power is delivered. This is just the things, the processes that produce parts and machines that then produce power. And this is, again, across the spectrum. Siemens is doing something really interesting at University of California at Berkeley, where they have a deep reinforcement learning for robots, essentially to teach themselves tasks. You can Google this and find some really incredible videos of robots essentially watching a single video of how to move one object from place A to place B, and then the robot figures out, oh, that's what the robot, need to do. I will move it from place A to place B. So there are really exciting things happening just at the front end of the power sector generally. And then all the way at the very, very bottom end, you've got devices like Google's Nest, the in-home thermostat, or Google Home, the home control speaker device. Philips Hue lights, which control how your lights are, it's an AI-enabled device which controlled whether your lights are on or off or at what sort of temperature they are. Lots of stuff going on across the system that will eventually impact power generation and delivery. Okay, so in utility operations, there are a bunch of applications for AI as well. So again, load forecasting or price forecasting, as Alejandro described, wind and solar forecasting. There's also predictive maintenance. And this is really where most of the interesting action is. So essentially, AI is used to forecast and predict and identify when a machine may fail based on a variety of different input variables. And this is done in a way that human monitor or machinist wouldn't necessarily identify. So for example, Duke Energy using Schneider Electric machine learning based predictive maintenance software, which is called Prism, they detected a little vibration in a turbine that would have otherwise gone unnoticed. And all it was a few bolts in a turbine of theirs that had come a little bit loose. And so this was an anomaly detection, right? The sensors within the machine picked up something that a human wouldn't have picked up otherwise, predicted that the machine would fail if these bolts weren't tightened. So tiny little things are predicted and saving utilities, millions and millions of dollars. AIs are also used for energy trading. On Wall Street, there have been some massive failures of specific trading or hedge fund algorithms, but they're getting better and better. And then one of the more common uses of AIs across utility operations now is in chatbots. So if your power goes out or your lights are flickering or you think there's an outage in your neighborhood, typically, you'll call someone and you'll have to wait online, or you'll have to wait for an operator to answer you. The chatbots, the natural language processing of the chatbots is getting increasingly better. That's all underlain by artificial intelligence. So again, not yet really in the actual delivery of energy, but everything surrounding the delivery of energy is also being enhanced by AI. A few standouts, at least in the United States, in this regard, are the New York Power Authority, which is a public power utility in New York State, NYPA, AES, which is based near me in Virginia. It's a global utility though, and Exelon, which is one of the largest utilities in the United States. NYPA, New York Power Authority, has an aim to be the first end-to-end digital utility, including building level energy control and predictive maintenance and control of their own utility fleet. AES is deploying a full spectrum, little by little, of AI things, including even sentiment analysis for their human resources team. They're doing safety based on AI-enabled videos of what's going on at the plants and drone-collected videos of what's happening on the wires. Again, across the spectrum. And Exelon, GE was their first customer for Predix, the GE brand of industrial internet software. APM is asset protective maintenance. So it's, again, this sort of anomaly prediction. They're using C3 IoT, another huge provider here, for fraud detection. So people illegally using their electric connections. So again, wide range of uses being deployed across the entire set of operations at utilities. Okay, now onto power generation itself and delivery. There are a few things that are being done. One of them is an example is at the GE digital wind farm. So basically, this is if you know a little bit about renewable energy, and I take it most of you know something about renewable energy, within a wind farm, there are multiple wind turbines, and the effects or the efficiency, production efficiency of a downstream wind turbine is often affected by the upstream wind turbine. The upstream wind turbine will take some wind out of the air. The downstream turbine will lose some of that wind. So one of the things this digital wind farm is optimized based on how the wind is coming in, which of the turbines are, how they're rotated with when they're on, when they're off. They'll also optimize which are the ones to get maintenance early. So this combination of different insights about how an individual turbine is operating within an individual farm, wind farm, has led to increases in energy production of up to 20% in some cases. So really, really remarkable. Siemens is doing similar things within their gas turbine fleet. I mean, GE is as well. Siemens probably has something on wind too. But again, these are sensors, and within the Siemens case example, these are sensors on the turbine blades within a gas turbine that are optimizing the flows within the gas turbine and again, improving the efficiency of those machines. And then there's a company called Next Tracker, which is built for trackers on solar farms. And the statistic I've heard is up to 6% increase in output from a solar tracking panel device. So these are pretty big numbers, increasing the energy production of turbines. On the delivery end, when you think about it, there are already lots of sensors across the power system. There are SCADA systems. There are PMUs that collect tons and tons of data on voltage and frequency. And applying AI, it's beginning to happen. Applying AI algorithms to those sensors we already have out there and those readings were already taken will gradually, and sometimes not gradually, lead to step changes perhaps in the efficiency and reliability of grids everywhere. Okay, but this is also happening at the demand side. So there's a company called STEM. Their tagline is Energy Super Intelligence. They have a system called Athena, and just to get a sense of how much data we're talking about, they report that they collect 400 megabytes per minute. This is spread across, I think, 800 different battery sites. So basically what they do is they have battery installations across a variety of different locations, usually businesses or commercial enterprises, and they do sort of an energy arbitrage and a price arbitrage with those batteries, the stored energy, and then the releasing of the stored energy, but they're doing it in a way that optimizes it for their clients using this AI. Tendril, another US-based company, has a series of demand-side management programs, and they collect data on sort of everything that a home user is doing, including the characteristics of the home, the occupant demographics, their utility bills, their partnerships with other devices, like if they're using a Alexa or Google Home device. All of these things, again, detailed data enabling customer and utility actions based on AI. I'm going to skip ahead a little bit here and talk. Oh, Belen is saying I don't need to skip ahead. Okay. So
take your time. You've got time.
I've got time. Okay, great. So on the grid control and electric vehicle end, I'm not going to go into too much detail. I'm going to note that there are three concurrent trends that are happening. One is electrification of energy generally. So this is this trend to use electricity as opposed to primary energy, natural gas, coal, whatever, in industrial processes broadly. The idea being that there are efficiencies that can be gained as the grid grows greener, as the grid has more and more renewable energy sources. Having an electrified energy system is going to allow us to reduce carbon more effectively. So that's one trend that's happening. It's also happening specifically within vehicles. China is leading on this right now with the number of electric vehicle buses they have, but many auto manufacturers across the world have declared their intent to produce electric vehicles, either all electric battery EVs or hybrid electric EVs. There's some car manufacturers that have declared their intent to move away entirely from internal combustion engine fleets. So those are being phased out. As the electrification grows, we're going to have more complicated load management needs. The system, grids everywhere, will get more complicated and more difficult to manage. As EVs penetrate, and there are some forecasts by groups like Bloomberg New Energy Finance that EVs are coming fast and furious over the next 20 years. As EVs begin to penetrate and people need to charge their cars either at home or during the day at work, those draw a tremendous amount of power. Again, the demand for a smart grid to understand when it's optimal to charge, how much value do you as the user have of having your car charged now versus waiting till the grid might have more flexibility on it and might be cheaper for you to charge, versus in fact allowing you to use or enabling you to use your car battery to supply someone else on the grid with backup power. It becomes increasingly complicated. AI is going to be deployed almost automatically, basically, with this increase in EV charging stations around the grid. There's a third trend which is happening, which is autonomous vehicles. Obviously, AI is the core of an autonomous vehicle, but many AVs are expected to be EVs, and there's a simple reason for that, which is that with an EV, there's less to control. You need much less computing power to control an electric vehicle than an internal combustion engine vehicle. And so the expectation is that as autonomous vehicles, AVs penetrate, they'll be mostly or majority EVs. And so again, increasing needs for AI to control this super complicated system. Lastly, I've got this acronym down there, SAVES, and quick poll before I say what it is, just on the chat. Tell me if you know what a SAVE is.
I really don't know, but EVs, I know what it stands for. Do you guys know anyone? Share in the chat.
No one? Or, I don't see it. So it is a shared autonomous electric vehicle. In other words, an Uber or a Lyft or a Via, one of the other companies that do car sharing. And the expectation of many urban planners and transportation planners is that if autonomous vehicles are not going to crowd our roads even more, then policies will need to be put in place to promote shared autonomous EVs. There are these two sort of scenarios that are being talked about for autonomous cars. One is sort of a dystopian disaster where we have internal combustion engine cars driving around endlessly and using even more KMT, kilometer miles traveled, or VKT, vehicle kilometer traveled, or vehicle miles traveled, VMT, with increasing congestion, increasing pollution, or this sort of utopian scenario where you've got everyone sharing a car and it's an EV and minimal traffic. So somewhere in between is the likely reality. But all of this calls for increasing use of AI with a definite effect and impact on the power grid. Okay, last slide. There's something that is being talked about now. It's pretty new. It's called an autonomous energy grid. And it's a little futuristic. It maybe is, where all of this is eventually going, the final frontier perhaps. The goal is a self-regulating and self-healing grid. So this is a grid that without any human control can absorb both the routine fluctuations and intermittencies from different kinds of power sources coming on and off, wind dying down, or sun being blocked by clouds, or sudden fluctuations in river current or something like that, to massive disruptions from storms or hurricanes or earthquakes. It's a grid that knows how to quickly heal itself. This is an enormously complex undertaking. The Department of Energy here in the US in 2017 issued several grants to different research organizations and different national laboratories, including NREL, National Renewable Energy Lab. So one of the main issues here is that there are different levels of complexity for different parts of the grid, and there are different timescales in which the grid needs to react, sometimes in milliseconds, sometimes in minutes, sometimes in weeks or months. But each of those timescales has a different level of complexity associated with it based on the resources that can be brought to bear and the costs involved. So tons of work left before we get there, but the fact that it's even being talked about is, I think, sort of exciting. So what does all this mean? More ones and zeros means less steel. In other words, we're going to build fewer power plants because we'll be using our power plants more efficiently. We're going to use less fuel. They'll all run more efficiently. Obviously less carbon, and certainly better reliability. As the machines will break less, the grid will have better voltage control and frequency control, and fewer outages. And that's it. Thank you.
Thank you very much. So I guess it's doing more with the same, or doing more with less over time, right? That's pretty much.
That's right.
Right, and uncovering, I suppose, new value, the same way that, Google managed to uncover new value for us, being able to find this value across different websites or data that is there, but it's difficult to find. Okay, I'm gonna ask you, Michael, to stop sharing your screen, if you may, please, so that we can see you guys a little bit more closely. We have a question here. Some have been answering. Actually, someone here made a comment. This is Arnold, someone that is well known to us here in Data Insights, a good friend for a while, for a long time. We know each other for probably more than 10 years. And he's saying that, the acronym SAEV is used by Tony Seba in the Transport as a Service report that you can download, and it's free, and it's pretty good, actually. Tony is someone also that I know for very many years, and yeah, he did this really great report on all of the autonomous things. But I'm not so clear. We even did a webinar here about autonomous vehicles, and it seems that the information is still thin on the ground, and maybe getting the government to approve of this kind of autonomous vehicles is not going to be so easy. Maybe a little bit more in the US, that is a little bit more forward looking, but it seems to me like it's going to be quite a fight here in Europe, and probably even worse in other places. But we can talk about that at another time. Let me just ask a question that one of them is sent. We have two questions here, and then I have a few of my own, if you don't mind, because this is a topic that really interests me. So Christian here says, as a first general question, I'd be interested to learn about where in AI we are currently at a global scale. We already talk about the existence of general AIs that can be thrown at any kind of problem, and that can actually write its own code. This is one of my questions. Do we have standard sort of softwares, I don't know what to call it, or solutions? And to which degree does AI nowadays write its own code? How far are we with the regulatory measures to control AI development and mitigate potential risks? So this is a very generic question. Maybe Michael, you take it first, and then we can go to Alejandro.
Sure. So if you ask, let me start with a little story, which is that I heard someone from AES describe their use of artificial intelligence at a conference I was at a few months ago. And he said, look, AI is what people who are crazy call it. The rest of us call it machine learning. So I thought that was sort of an exaggeration, and it wasn't, nor was it, really, really precise. But what he meant was the movie industry has painted AI as these totally aware, sentient robots that can do everything. And we're nowhere near that yet. If you speak to AI scientists, they sort of shake their heads and roll their eyes and say, this is not happening anytime soon. One person said something along the lines of, it's akin to worrying about overpopulation on Mars. It's just far away. On the other hand, there was a survey done, I think it was 2 years ago, of AI scientists when they expect artificial general intelligence, AGI, or human level machine intelligence, HLMI, to actually occur. And there was a range. And at the far end of the range, it was like 80 to 100 years. And at the near end of the range, it was about 20 years, I think. Sort of the very, very nearest it could possibly be was 20 years. So to me, 20 years is sort of, it's effectively tomorrow. I mean, if we were trying to prepare our society for something as radical as 20 years from now, or something as radical as AGI in 20 years from now, we should have started 10 years, because it'll have really dramatic implications on how the world functions. I hope that we're farther away from that, but I think we can't discount the possibility that it'll happen sooner rather than later. One of the things that I take away from all of the surprises we see in specific AI, like I mentioned at the beginning, the Go game win by the AI was unexpected. The scientists keep on getting surprised by how quickly AI progresses and how dramatic its advances are. So to me, that's a lesson. We shouldn't be surprised by surprises anymore. I don't think we're nearly there yet, but some of the learning is exponential.
I was just thinking that all of the AI is going to be based on the data we can collect. And by my experience, I work with data marketing, and the data is often not great. I mean, even when you make an effort. So if you don't start by gathering the right data and almost near perfection, you're going to get the wrong solutions, I suppose.
I think that's generally right. There's a field, or there's a trend towards using unstructured data. And maybe Alejandro could talk a little bit more about that. But basically the idea is some of the algorithms are being trained to take in messy stuff and kind of make sense of it. And sometimes they do a decent job of figuring out what it all means.
I can tell you, everyone is super scared of what Facebook knows about me. Right. For a very long time, I was thinking, if I look into what Facebook knows about me, they'll be wrong about 50% of the time. And then there was a New York Times article a while back, they looked into this, and the woman actually found that it assumed so many things that weren't true. That was really interesting. Alejandro, sorry, let me...
Yes, of course. First, what Belén was saying is correctly for all artificial intelligence, is that the data must be filtered in very high details in order to be able to use it properly for artificial intelligence. And also, on the other hand, we see artificial intelligence as a new trend right now. All companies are looking at this like it's something new, when artificial intelligence has been around for several years. We have been using continually for over 20 years next year. So there are several companies that have very much experience with the artificial intelligence in the forecasting sector, only for forecasting. It's one of the main applications of artificial intelligence. Yes, it's not a trend. It's something that has been developing for several years. And as Michael was saying, it's growing with great steps. And we will be looking at more results for the next few years, of course.
I suppose a good indication, correct me if I'm wrong, for companies looking at possibly artificial intelligence should be like, do you have a process that you want to make more efficient? Then look into how artificial intelligence could do it for you, but not necessarily dive in, you know, unless there is something like that. Michael, seems like you want to comment on this.
Yeah, I mean, I think one of the things that a lot of AI scientists sort of find annoying is that when something seems like magic, then it's AI. And when something is sort of regular use, it's not AI. So most of the stuff on our smartphones is AI enabled, but no one thinks that they're carrying around a piece of magic or a thinking robot or a sentient. So that, I think that's just what I would say.
I would agree with you until I saw those new phones that you take a selfie and you look like a model, you know, and then I just thought, you don't even need to put makeup on anymore. You know, you can just, so I think it's definitely, we're in little pockets, we're seeing a lot of advance. Let me see, there's a couple of questions here also. On the photovoltaics industry, can I use the presented methods to the present methods to detect open circuit faults, inverter fails, and generally predict underperformance? So you mentioned a few people that are already doing this type of thing, right?
Yeah. Again, it depends on where on how many sensors you have and where, but I think for me, the takeaway from sort of assessing the AI landscape is that wherever there's an event, as long as you have data on it, and as long as you have sensors that'll capture one of the representations of the event, and you have enough data to analyze it, then you can use AI to predict the future ones. Yeah, there's this company Next Tracker that optimizes the tracking systems on a solar plant, on a solar field, but it can be used kind of anywhere. Alejandro, do you agree with that?
Yeah.
Yes, of course.
Okay, so someone's here saying that they're visiting a mine in November that is using autonomous mining trucks. So that's very, very interesting. I think possibly actually it might be easier to get this in a closed circuit than where there is like interaction with people that are outside. But we you know, by all means, Arnold, come back and tell us, take a couple of videos and pictures, and we could actually talk about this in a webinar as well.
Yeah, you know, I didn't talk anything about upstream, but AI is of course being used in oil and gas discovery and in coal mining. I mean, it's being used. I decided just for the sake of brevity, I wouldn't have a slide on that, but it's being used everywhere in the energy sector.
Yeah, we can revisit it. You know, again, we can do another one in the future, more looking at that side. Could you please elaborate on the Vietnamese GE case and how to apply AI to improve manufacturing? This was one of yours, I think.
Yeah. So, I mean, basically, it's the same principles as would be applied in the power sector specifically. So GE has this platform that they call Predix. When they first rolled it out, I should say, by the way, that I used to work for GE. I stopped working there about a year ago. When they first rolled out Predix, they were trying to bill it as the OS for industry, the operating system for industry, sort of like an iOS. Predix is meant to be the OS for the industrial Internet of Things. And so the idea is, within a factory setting, you have a series of machines that have different behaviors and different anomalies. And you can apply the same sort of machine learning techniques to how your machines are operating, how your supply chain is functioning, how the individual workers on your floor are moving from place to place. And so you have these, the GE buzzword or slogan or whatever was a brilliant manufacturing system. So again, applying smarts, AI smarts everywhere that you can improves your productivity. One of the other terms they liked to use was the digital thread. So the thread connecting all the different pieces of a manufacturing system. Those different elements get smarter the more they know about each other and the more they can be, they can be optimized.
Thank you very much. There's a couple of questions here for Alejandro. One says, what features did you use for the time series forecasting in your models? Also, what error levels did you get on your test sets? It's a very specific question.
Yes, I wanted to integrate a question with a follow-up question, which is, what is your opinion about AI?
That was going to be the next one, so you integrate
yes.
it, perfect.
Yes, I will integrate it and use an example to answer this question. But the second question was, what is your opinion about AI for solar and weather data forecasting in solar energy industry? For experience told us that it has not worked well. In this case, both questions can be answered with the problem to forecast weather at a couple of days ahead. So we have a great weather forecasting system for the next few days, but when you go for the next weeks, it doesn't work well. This affects for the demand forecast, the solar production forecast, the maintenance, but practically all forecasts. So in this case, I wanted to use an example, an application we developed for the Norwegian TSO, Steiner. And we had several data. We have temperature, wind speed, solar radiation, and individually, all these data were not directly correlated with the specifically quality that we need. Were not related directly with the load forecasting, but when we integrated, we calculated, for instance, a new variable that we call wind chill. Is the most important variable for the Norwegian regions because the temperature is not what affects the demand the most. So this variable only works for the next 2 days, but then from the third day ahead, you have to work with indexes obtained from historical data. So if there is any event that is not possible to forecast, so the error is increases. So you have to analyze it for horizons, not in the short term, but also in the midterm. You work only with indices obtained from the historical data. That's why the second question mentioned that the solar production is not being great with the forecasting, because any variability in the weather in the region affects directly to the impact, and the cloudiness is one of the most difficult weather variables to forecast correctly. That's why we can provide any error in the general term, because you have to analyze the region and the variability of the data. So the error is different for each region.
Thank you very much, Alejandro. I worked a lot extensively in CSP, and this is definitely the case with them. You know, they have to be getting almost every 10 minutes, you know, the latest forecast. And it's incredible how we've come so far with so many things, and we still can't tell what weather we're going to have tomorrow. So one more question here. And this is for an electronic engineer, someone writing saying, and a field service engineer. What kinds of technical skills or important new knowledge is necessary in AI to get oneself up to date with the technical market and to give outstanding professional service to clients in the present and the future? In other words, how can I, as a professional, you know, make sure that I am up to date and leading the way with AI? Any advice for Tommy?
You know, I think there are a few things you can do. Obviously, there are a lot of online courses to, you know, you can learn how to program, but it doesn't sound, you know, in TensorFlow or whatever, you know, there are lots of different AI online courses you can take. It sounds like for your role, maybe it's more useful to just be aware of what's happening and what sorts of AI-based techniques will help you do your job, complement the field service engineer task, right? So I don't know what company you work for, but my guess is that they're already thinking of ways to do predictive maintenance before a field service engineer needs to repair a problem. So I would start by being aware of what your company is doing at the back end.
Do you want to add anything, Alejandro?
Yes, also I want to recommend that you see the optimization methods that are around and see it because artificial intelligence can be very helpful to integrate several methods and obtain specific to the needs of your company.
Thank you very much. And now two of my questions, okay, and these are kind of specific but also general. One is, you know, The Economist keeps having these articles about the global artificial intelligence sort of race or battle or whatever, and seems that it's pretty close between the US and China, but China's throwing a lot more at it. Europe is nowhere to be seen, even though they've thrown millions at it. They've done a really poor job with it. At least that's what it says, you know, in The Economist, what they say. What is your view? Do you think that we are going into one direction, there will be a winner takes all sort of thing?
I think there's a possibility. One of the fears of the folks who are worried about artificial general intelligence, AGI, is this winner take all scenario, that there's a race to AGI. Again, I think that's farther away. So, but you can imagine that in a winner take all scenario, having the first AGI would be dangerous if it falls into some sort of rogue actor. I think that China has some advantages over other countries. One of them is the scale at which they're deploying AI. They have a national level artificial intelligence strategy that is being, you know, they're supporting their industries in the same way that China has always supported their industries with, you know, lots of state support. But they also, frankly, have much more control over what data is available and what data is accessible to these companies than European countries or the US do. And so in that regard, I think China has advantages that US and Europe don't have.
Oh,
Alejandro?
I'll pass on this one.
I'll note that there's a trend.
It's very political, you know. Alejandro's like, I'll pass on this one.
I'll note that there's a trend of Chinese scientists or students coming to the U.S. to study AI and then returning. And there's another trend that is, you know, people are wringing their hands over a lot of deals that the Chinese government enforces on foreign companies in terms of what they have to give up in terms of their intellectual property. There's an imbalance that is often, you know, the source of much discontent.
We will see what happens. We will watch this space for sure, but it's an interesting one because, you know, if it's one of the situations where you end up following one solution, then there might be like the geopolitics or the geoeconomics, I suppose, may change in the future. So last question, I wasn't going to ask it, but we have 4 more minutes and there's a question here. It says, how do you compare GE Predicts with Siemens MindSphere or a similar ABB product? It's a question by Faisal. Yeah,
I mean, no longer being at GE, I don't have a dog in the, you know, I don't have a horse in the race anymore. So I'll pass on that one. I think they're all excellent companies and they all have their plus and minuses. I'll punt.
Fabulous. Maybe Alejandro wants to answer this one.
Well, it was directed for Michael directly. Sorry.
Excellent. Well, thank you very much, Alejandro. And thank you very much, Michael. It's been a pleasure to learn a little bit more about artificial intelligence. This is a long road, unfortunately. This is not going to change overnight, but I'd like to just thank you both for sharing your knowledge with us. Hopefully, you know, in a few months from now, we will do an update and we'll find out a few more things and we'll learn about how companies are using it. At the moment, everything is very secretive, but it's only a matter of time before best practices appear. And thank you very much for everybody in the audience and see you next time. Bye.
Thank you.
Thank you.
Bye.
Bye.